This PhysCast is going to look at how to normalise a quantum mechanical wave function. The example given here is for the 1D infinite square well, and the question is asking you to find the normalised spatial wave function for the n equals 4 state. So a quick sketch to remind ourselves of the system that we're looking at. If we were to think about the potential energy of this system as a function of distance here, our infinite square well, at least one that's nicely symmetrically placed around the origin, which is one we've looked at in class, might go, for example, from some minus a over 2 distance to some plus a over 2 distance, small a there, where basically the potential is infinite outside of that range. So we might say there that the potential energy there actually goes to infinity whenever the absolute value of x here is larger than a over 2. And that leads us to say that the particle in our infinite square well here actually is excluded from those regions. It's constrained to stay within that minus a over 2 to plus a over 2 range. And as we discussed in lectures, that tells us that the wave function, the spatial component of the wave function at least here, must be 0 for that condition there, whenever the absolute value of x here is greater than a small a over 2. And we also went through and found the solutions for inside this infinite well, and turned out there were only certain allowed solutions there for our spatial wave function, the spatial component of our wave function here, and we could write those, for example, one set of them, we might write some arbitrary constant here, capital B, multiplied by the cosine of n pi x divided by a, where n here was an integer. In fact, it had to be an odd integer, 1, 3, 5, 7, etc. And there was another set of solutions here with another constant, another arbitrary constant there, in this case capital A, we might have written it in class, multiplied by a sine function, the sine of n pi times x divided by small a there, where now this was the case when that integer had an even value, etc. And so this question is asking us about the n equals 4 state. So for that n equals 4 state, we can say straight away that our wave function is going to look something like some number here, capital A, multiplied by the sine of 4 pi x divided by small a. And importantly, this wave function here, this part, is actually time independent. You might remember that the full wave function here, capital psi of position and time, is this spatial dependent part multiplied by some time dependent part that will actually be e to the minus I times the energy multiplied by time divided by h bar. And so we're only really interested in this question here, in this spatial component here. Now to normalize, you can see we've almost got that wave function. What we need to know is what value must this capital A here have, this constant at the front here, to make this wave function normalized. And then what we mean by normalized is that the integral over all space of the modulus squared of the wave function, so let's square that, integrate over all space from minus infinity to plus infinity there, must equal 1. And remember, that's important because that means we can actually interpret this mod squared of our wave function dx as a probability distribution. So it's got a probability of 1 of existing somewhere. That's what we mean by the existence of our particle. Of course, you can see from our expression here that the psi star psi, taking the mod squared of this wave function here, this time-dependent part, this complex exponential here, will actually multiply through to give 1. So in fact, to make this normalization here, all I really need to do for this problem here is integrate the mod squared of the spatial part over all space and set that equal to 1. Then I will have normalized the complete wave function, and I'll know what this normalization gives me for this value of capital A at the front here. And of course we did something similar in class, and here's another example with a slightly different energy state here, the n equals 4 state we're doing in this case here. So what we want to do is we want to say the integral in this case here, and you can see integrating over all space is kind of easy to do for the parts of space that are outside the infinite well. Out here the wave function is identically 0. So that's kind of an easy bunch of integrals to do. We're just going to integrate 0 from minus infinity out to minus a over 2, and then we'll also be integrating 0 squared from a over 2 out to x equals infinity. So all I'm really left with as a calculation is to go from minus a over 2 to plus a over 2 of the square of this a squared, capital A squared, sine squared 4 pi x over a, integrated over all space. And I can write that with that a squared out the front if I like, because that's just a constant. Remember, that's the constant whose value we're trying to determine to get ourselves a normalized wave function here. And then there's a couple of things I can do that basically we just want to do this integration, and you might have some integration skills that allow you to do that quite easily, but you might have different ways of doing it to me, and that's fine. One way to think about this is because I'm integrating essentially here sine squared of 4 pi x over a with respect to x. This is a nice even function. What do I mean by that? I mean that if I was to think about what this function looks like as a function of x, around x equals 0, actually sine squared looks something like this out for positive x. It also looks exactly the same out here for negative x. And I can see that for any particular value of this function out here at some positive value of x, if I go the same distance out for a negative value of x, I get the same value. This is an even function, which means if I'm integrating symmetrically with respect to x, if I integrate, say, from here out to here, whatever values I get out here for my integration, I'm going to get the same values out here as well. And so I can do a fairly straightforward simplification in my integration by simply saying I can do, if I want to, twice the integral here from 0 to a over 2. You don't have to do that, but that's a nice simplification that can sometimes help. And then now I simply need to know how to integrate sine squared of some function of x dx, now between 0 and small a over 2. And there's various ways you might choose to do that. You might integrate by parts, or you might use the double angle formula to rewrite sine squared just in terms of sine or cosine. Or you might look up, for example, if you were doing this in an exam, you might have a formula sheet that told you something along the lines of the standard integral of sine squared of, say, some multiple of x, u of x dx. Turns out you can write that fairly straightforwardly as x divided by 2 minus the sine here of 2 times u times x, all divided by 4 times u, plus some integration constant, which we won't bother because we're going to do a definite integral here. And in our case here, we're going to use exactly this kind of integration. And for us, we're going to basically have u here is going to be equal to 4 pi divided by a. That's what our u would be. So with that notion of that standard integral that I have there, I should be able to, let's just give ourselves a little extra room to draw here. I should be able to do this integration fairly straightforwardly. What I'll have here is I'll have 2 times a squared, capital A squared, at the front, and the integral here will be x over 2 minus the sine of 2u times x. Remember, our u here is that, so it's going to be the sine of 8 pi x over a divided by, or 4 times u, which would be 16 pi divided by a. I'm going to evaluate that between small a over 2 and 0. And that should be fairly straightforward to do. I can again keep my 2 times capital A squared out the front. When I'm doing it for small a over 2, I'll end up here with small a over 4 when I divide by 2, minus the sine, and you should be able to see if I do 8 pi over a times a over 2, I'm going to get 4 pi there. I'm going to divide that by 16 pi over a. And I've got to subtract off, of course, this thing evaluated at x equals 0, and you should be able to see that 0 over 2 is 0, and in fact sine of 0 will also be 0. So that second part there is easy, and that's partly why it's actually an easier calculation to take into account. Instead of going from minus a over 2 to plus a over 2, I must get the same result as doing twice, just from x equals 0 to x equals small a over 2. This is my kind of simplification by taking into account that function that I'm integrating here is an even function being integrated symmetrically about x equals 0. And so this should be fairly straightforward. Look, of course, I can also see here, I probably almost forgot to mention, sine of 4 pi, of course, is also 0. So what I simply have left here from my integration is 2 times capital A squared multiplied by small a divided by 4, which of course you can see there will be small a times a squared over 2. Now, of course, I'm trying to normalize, so what that means, of course, is I want this thing to equal 1. So I want this integral here to equal 1. I'm looking for the value of capital A that allows that to happen. So that will, of course, give me capital A squared must equal 2 divided by small a, or capital A must be plus or minus the square root of 2 divided by small a. So my final statement I can make here is that my normalized wave function, spatial component of that wave function for n equals 4, is going to equal root 2 over small a, actually plus or minus that, times the sine of 4 pi x over small a. And that's my kind of final normalized result. And I should think about what that tells me, so let's draw a quick little diagram here of what we might think this wave function is going to look like. Here now I'm drawing that spatial wave function as a function of position, where again perhaps this is minus a over 2 over here, and this is plus a over 2 over here. We know from our physical understanding that the wave function is 0 outside of our well, and this is telling us that we've got this sinusoidal wave function in here for our n equals 4. I'm not going to be particularly good at drawing this, I probably haven't given myself enough space, but of course it's going to have 4 oscillations in here. Remember, my n equals 1 has 1 oscillation, my n equals 2 has 2 oscillations, it's going to have 4 oscillations in here, so it will have 2 over this side, and it will have, again I haven't drawn it particularly well here, and it will have again 2 over this side, something like that, rather badly drawn, and that would be the case if I use the plus sign in my my normalization. You might wonder about what's that minus sign telling us. It's simply saying we could do essentially the inverse of this, and we could have our wave function basically doing this kind of green curve I'm trying to draw in here. Again, not particularly well, I'm afraid, but basically that would be the exact same wave function. I don't really care about this plus or minus. Remember, my calculations normally involve the square of my wave function. So as long as it's got its nodes and antinodes at the same location, I really don't care whether they're positive or negative. That normalization condition is really telling me that my largest and smallest values here are of course root 2 over small a and minus root 2 over small a. And so there's my normalized wave function for my n equals 4 state for a particle in the infinite square well.